Hello everyone. In the previous lecture, you studied that the operating system acts as an interface between the computer hardware and the users. The operating system also acts as the manager of the computer hardware. You must be wondering how the operating system does this task. In other words, how the operating system helps the task of acting as an interface between the user and the computer hardware. The operating system does this with the help of system calls. System calls are special programs that are invoked whenever a user has to interact with the hardware associated with the computer system. Operating system provides these system calls. Before we can go deeper into how the system calls work and what are the different types of system calls, let us understand the concept of system calls with the help of an example. Suppose you want to write a simple program of copying the text of one file to the other. So suppose we have the file f1.txt and you want the contents of this file to be copied to another file f2.txt. You want to write a program so that you can read the contents of this file and copy those contents into the other file. For doing this task, there are some essential requirements. First of all, you would like to know the names of the two files. First, the file to be read. You can either have the names of the files beforehand while you write your program, or you can ask the user. The simplest method or the most common thing that you might want to do is to ask the users of the program to tell the name of the file. Suppose you resort to this technique. For doing this, first of all, you will print on the screen console for the user to enter the name. Then you would require a program to read the input text given by the user through the keyboard, which again will be done through a system call that would access the contents that were written through the keyboard. Then once you have received the names of the two files, then you will open the first file, that is the f1.txt. Opening this file again requires a system call because you would access the hard disk associated with the computer system. Now, this file might exist or might not exist in the system. Suppose the file does not exist. In that case, there would be an error. This processing again requires a system call. Suppose there is an error, then you would like to inform your user that there was an error while opening this file. This you would do with the help of printing a message on the console, which again requires a system call. Suppose on the other hand that the file existed. In that case, you would read the file from the hard disk and store the contents into the main memory. This again requires different system calls at each step. Once you have opened this file successfully, then you would go to opening the second file. This file might be created, or if a file with this name exists already in the system, then there are different things that can be done. We might give an error message that the file, instead of being created, the file that we are trying to create is already existing in the system. In that case, we either can abort the process, or we can delete the content of the existing file and copy the contents of the new file into it. Both these steps require different system calls at each point. Once you have created the new file and opened the first of the file, then there would be a loop, and through this, every time a character from the file 1 would be read and it would be written to the other file. This process would continue until we reach the end of the first file. This again requires system calls at every step. After this, we will check for any errors that might occur in the process, and then the files would be closed. Closing the files will again require a system call. Thus, you might have understood that even a simple program of copying the contents of one file to the other requires a series of system calls. Why? Because every time you are accessing one or the other resource or the hardware associated with the operating system. And these system calls are the interfaces that are provided by the operating system for accessing the hardware. We have seen what system calls are and why are they useful. Since the operating system provides all its functionalities with the help of system calls, the types of system calls are closely related to the functionalities that are provided by the operating system. Thus, the different types of system calls can be grouped according to the corresponding functionalities that are provided by the operating system. The system calls can be grouped broadly into 6 different types. These are process management, file management, device management, information maintenance, communication, and protection. Let us discuss each of these types in some more detail. You can see in the chart here that the first of the system calls provided by the operating system is related to process control. As you know, that a program in execution is a process. While executing, we may need to end or abort the process. There is a difference between end and abort. A successful completion of a program corresponds to ending of the process. While if a program has to be stopped eventually at some point due to some error or due to some other problem, then it is called as an abort operation. Similarly, a program while running might need to load or execute some other program. System calls are provided for doing this task as well. In other cases, a running process might create a child process. This child process then runs and completes its execution. For this, there are system calls that are related to creation and termination of a child process. Then, when a process is created by another process, there are certain types of attributes that are associated with it. The parent process must have the ability to control the execution of child process. This can be done with the help of setting the attributes related to the child process. For this, there are system calls that are related to getting and setting the attributes related to different processes. Then, a process might wait or signal for an event. Like a process might be waiting for its child process to execute. This can be done with the help of system calls related to wait and signal of events. Finally, processes might also allocate and free memory, and system calls are provided for doing this too. Now let us move to file management. As you know, one of the important part of operating system is to provide help in accessing the information that is stored on the disk in terms of files and directories. For this, different types of system calls are provided. These can be grouped as the system calls for creation and deletion of file, for opening and closing files, and then when you have opened a file, then you might need to read the content of the file or write something into the file, or read something or write something at some particular point from in the file, which can be done with the help of the reposition attribute. So these read, write and reposition system calls are also provided by the operating system. Then again, there are attributes related to files that are stored on the disk, and there are system calls for getting the values of the attributes or setting the values of the attributes to some value. Then there are system calls for logically attaching and detaching different devices. The next type of system calls are related to device management. As you know, there are different types of devices associated with the operating system. For managing each of the devices, different types of system calls are provided. These system calls are like calls for requesting and for releasing some device. Like a process might be accessing the console for printing the contents on the screen, or maybe accessing the printer for printing the results of a program on a page that is physically attached to the printer. For this, the process need to access the corresponding devices, and therefore request and release device system calls are provided. Similarly, read, write and reposition system calls are provided for the device management as well. And then the get and set device attributes, and then logically attaching and detaching devices to the operating system or to a certain program are also provided by the operating system. You can see that file management and device management system calls are closely related. In some of the operating systems, instead of providing different system calls for file and device management, there are common system calls for doing these two types of tasks that are related to file and device management. Actually, this is a design issue whether different system calls are to be provided for file and device management or whether they are going to be same. Next, we move to information maintenance. Some of the information needs to be stored about a process when it is running. Also, information related to devices attached to the operating system and other information are also required. All this is done with the help of system calls that are related to information maintenance. So there are system calls that are simply provided to maintain some of the information related system. Let us see some of the examples of system calls related to information maintenance. We can see here that there are system calls related to get and set date and time. So a process might need to access the current date or current time at some point of time during its execution. This can be done with the help of system calls. Further, there are system calls for giving information such that the amount of free memory or the number of devices attached to the operating system or the version of the operating system. All these things are done with the help of the system calls that can be grouped into the category of information maintenance. Again, the fourth category of system calls is communication. As you know, running processes might need to communicate with each other. This communication may be done in two ways. This can be done either through message passing or through information sharing using shared memory. In message passing, the two processes or the two computers communicate with each other by sending and receiving messages to each other. For doing these types of tasks, a communication link needs to be established between communicating processes. Create and delete communication system calls are provided for doing this. After the communication link has been established, the messages can be exchanged. For this, system calls such as send and receive messages is also provided. Then there are system calls for terminating the communication after it has been completed. While communication, it is not necessary for the two processes to be residing on the same system. The processes may be on two different systems. In this case, we say that the two computers are connected to each other through the communication network and information is exchanged between them. there are system calls which are provided for these types of communications as well. The other type of communication is through shared memory. In this type of communication, two processes exchange data with the help of a shared memory area. The information that has to be shared is kept in this memory, in this part of the memory, and the processes that are sharing the data can access it through that shared part of the memory. In this type of communication, it is important to provide protection to the shared area of the memory and also controlling the access of processes to this shared area. System calls are also provided for communication by this method. We will see that in detail in later lectures. The last type of system calls that we are going to discuss here is protection. You know, in a multi-programming system, there may be more than one programs are running on the system, as well as if there is a multi-user system, there are more than one users that are accessing the system at the same time. In such cases, it is very important to provide protection to different processes as well as different parts of memory and devices that are accessed by different processes. For providing this protection mechanism, there are system calls that can be grouped into the category of protection. There are system calls for getting and setting permission to access various resources. Like a file may be set to read only. In that case, a process can only read that file and cannot change the contents of the file. Similarly, there are system calls for allowing and denying users from accessing some of the resources associated with the operating system. All the types of system calls that make these things possible can be grouped into the category of protection. We have seen that the operating system provides system calls for accessing the computer hardware. However, these system calls are dependent on the associated hardware with the operating system, and therefore, when the hardware of the operating system changes, like if you change your printer, the associated system calls will also change. In such a case, it would be very difficult for a programmer to write programs for each and every device. And every time the device changes, the associated codes need to be changed. This is a very difficult situation. And in order to answer this problem, the operating system provides libraries or the inbuilt functions that are known as the application programming interfaces or the API. These are the specific functions provided by the operating system that can invoke the system calls on behalf of the user. So the user has to only remember these APIs. Every operating system provides these libraries that can be accessed whenever a program has to invoke a system call. And these programs actually take care of the associated hardware with the operating system, and therefore the users don't have to remember the associated system calls for every device that is attached to the operating system or the physical computer. There are certain examples of APIs like POSIX threads and the Windows API that is provided by the Microsoft operating system. These APIs make programming tasks easier and can be used for accessing the system calls without taking care about the associated hardware of the computer. We will now discuss in detail about some of the design goals of the operating system and how the operating system is actually implemented and what are the different types of operating system. Having seen the role of system calls in acting as an interface between the computer hardware and the users, now let us focus our attention on various design goals associated with the design of operating systems and how the operating system is implemented. Like any other system, designing the operating system also requires having certain design goals for the designers of the operating system. The design goals of the operating system could be broadly divided into two categories. There could be broad design goals for the operating system, like when trying to design an operating system, we might first of all think about it like whether it is going to be a single user system or a multi-user system, or whether it is going to be a real-time system or a distributed operating system. All these types of things, when they are decided, they actually decide many of the functionalities that are associated with the operating system. Once you have decided these broad design goals, further specification of the goals of design are rather difficult. Although these goals can be divided into certain types of requirements that might be expected by the users of the operating system as well as the designers of the operating system. Like the users might want the operating system to be easy to understand and use, they might want it to be fast and reliable, among other things. Similarly, the designers of the operating system would be more interested in designing the operating system in such a manner that the design itself is easy to understand, as well as the design is flexible so that new functionalities may be added into the existing system with least effort. Of course, they would also want the system to be fast and reliable. However, there are some problems associated with defining goals in such a manner. Why? Because we don't know how actually we are going to achieve these goals. There is no consensus on that, as well as there is no set procedure that might be followed to achieve these goals. What actually is done while implementing the operating system is that some of the design goals that are decided in such a manner are tried to achieve, and the operating system is improved one step after the other once it has been implemented. Thus, the broad design goals like designing a multi-user or a single user system, a distributed or a real-time operating system and such are decided beforehand, while other things are implemented one after the other as the feedback is obtained from the users as well as the designers of the operating system. While studying the design goals of the operating system, it is also important to understand the difference between policy and mechanism. Policy tells us what is going to be done in the operating system, while mechanism tells us how that can be done. A good design of operating system is one that separates as much as possible the design and the mechanism of the operating system. For example, in our previous lecture, we have studied that in a multi-programming system, the CPU selects one of the processes present in the main memory for execution when it is idle. Selection of a process is dependent on a selection methodology or a selection procedure. On the basis of the procedure, one of the processes in the ready queue or in the main memory is selected for execution. What policy is to be followed for selecting a process is a policy matter. However, how those processes that is on higher priority will be selected is the mechanism. A good operating system design would be that designs the operating system in such a manner that any policy can be implemented on the same mechanism. Having studied the different types of design goals associated with design of an operating system, now let us focus our attention towards how the operating system is actually implemented. Like any other program, operating system is also a set of programs. Operating system comprises of a set of programs. these programs are usually written in some high-level language like C or C++. Why do we use a high-level language such as C or C++? There are certain advantages associated with using these languages, such as these languages are easy to code and debug. As most of you who are listening the lecture might have some idea of programming in C or maybe in C++. So you all must be knowing that it is rather easy to code in C or C++ than it is in a machine level language like the assembly language. Further, the code written in C or C++ are easy to understand, and therefore, once the code is written for the operating system, it can be understood by other programmers as well if they want to make certain changes or they want to make improvements in the code. And therefore, it is important to write in a high level language so that to improve the understandability of the code. Also, programming in a high level language is rather compact than assembly language code, and therefore, the operating system, as it comprises of a large number of programs, programming the operating system would be very compact if we use a high level language. Also, the code can be written faster in a higher level language. What could be the possible disadvantages associated with using a high level language for programming the operating system? Well, the only possible disadvantage that could be associated with programming with a high level language is reduced speed and increased storage requirements. See, assembly language, when you write your code in assembly language, it is closely associated with the computer hardware, and therefore, it requires less time to execute. When you write the same code in a higher level language, then many types of translations are required before the code can be executed, and therefore, usually running the code in a higher level language reduces the speed. Further, the code requires increased storage because of different types of function calls and APIs associated with the code. The storage requirements nowadays is not a bigger factor because the storage technology has improved greatly and the cost has reduced a lot, and therefore, two of the possible disadvantages, the reduced speed and increased storage requirements, one of them, the storage requirements, can be considered to be removed simply because of the lower cost technology that is now available to us for designing the operating system. However, the point of reduced speed is still of concern. How do we address this? Well, it is important to understand that operating system has a lot of programs associated with it. All the programs are not running all the time on your system. Thus, there are certain programs that keep running all the time are critical to the performance of the operating system. These programs can be identified. Further, when we write the codes of the operating system, we can, if we don't know beforehand, we can use some kind of techniques to find out the bottlenecks that are causing the system speed to reduce. These bottlenecks can then be converted into equivalent assembly language code, and thus the speed requirements, the speed issues can be reduced. Of course, for understanding the bottlenecks, we need to monitor the system performance. How do we monitor the system performance? The system performance can be monitored by keeping, say, logs. Most of you must be knowing that the operating system keeps log of the activities performed by different processes on the system. Important points or important events while executing a user or a system program are always recorded by the system in a system log. This system log can later be read by the designers of the operating system for making better designs, as well as finding out the bottlenecks and then converting that code from a high level language to a lower level language such as your assembly language. Most of you must have some idea about the data structures. If you had studied that, you must be knowing that the most important thing for deciding the performance of a program is the data structures and the algorithms associated with the program. By wisely using the data structures and designing better algorithms, we can achieve performances that are actually not achieved by the corresponding hardware support. And therefore, without paying attention to writing programs in a lower level language, we might focus our attention to getting better data structures for designing the operating system as well as using better algorithms. The structure of operating system has evolved over the years. It has evolved with the help of evolving technology, that is the support from the technology of the hardware, as well as the feedback that was obtained from the users of the operating system, as well as the designers of the operating system. We will start our discussion of the structure of operating system with the simplest structure. This is the oldest structure that was designed when the operating systems were initially developed. The examples of such structures is the MS-DOS operating system and the original Unix operating system. The design of these systems was limited by the hardware technology that was available at that time, as well as the functionalities that were associated with the operating system. These systems were designed with the single goal of providing all the functionalities that are to be supposed to be associated with the operating system in as compact manner as possible. Therefore, these systems were not carefully divided into modules. There was no clear-cut interface between different functionalities that were provided by the operating system. Further, there was not much protection of the hardware among different designs of the operating system, and also the protection of different user processes and the system processes. Let us discuss the MS-DOS operating system structure. As we can see, we have application programs that are at the top of this structure, and at the bottom level we have the hardware associated with the operating system. In the middle, we can see that there are resident system programs which can access the MS-DOS device drivers. We can see here that the application programs can access these resident system programs which act as an interface between the system hardware and the application program. However, the most important thing that is to be noted here is this part of the figure. We can see that the application programs can directly access the hardware associated with the system. Similarly, the resident system programs can also directly access the system hardware. This is not a very good design. Why? Because application programs accessing to hardware might cause system crashes. Suppose a program fails because of errant programming or maybe because of some malicious programming. Then the entire system may get crashed because it can directly access the device drivers. Therefore, there is no protection that is provided to the system hardware. While such a programming made the operating system very compact and easy, but it did not provide any kind of protection to the hardware, and therefore such a system was not very useful. Let us now discuss the structure of the original Unix operating system. The original Unix operating system was different from the MS-DOS system. Basically, The difference was that there was a kind of layered structure that was implemented in this system, which was not present in MS-DOS. All the functionalities that were supposed to be provided by the operating system were grouped into one, and that was called as the kernel. As you can see, in this structure also, at the top level, we have the users of the computer system, and at the end, in the bottom, we have the terminal controllers, device controllers, memory controllers, and then the hardware. In between, we have the kernel interface to the hardware, and then there are system programs such as the compilers, system libraries, etc. And the functionalities that are critical to the operating system and that are specifically associated with the operating system are all grouped together into what we call as the kernel. We will discuss more about the concept of the kernel later in this lecture. But here, what is important is to understand that whatever functionalities that we suppose to be present in the operating system are all grouped together, and they are present as the kernel as a separate layer in this system. This was the original structure of the Unix operating system, and it was layered. Here, some kind of protection is there because the user programs cannot directly access the hardware. There is a kernel interface which acts as the interface between the hardware and the users. However, this system was also not free of errors. Why? Because the functionalities that are associated with the kernel are not grouped into modules very carefully. There are not specified interfaces between the modules, and the functionalities are too much for the kernel itself. We expect the operating system to have clear-cut functionalities, and the functionalities provided by the operating systems are also expected to be reduced in the manner that they are manageable. So this kind of a system in which the kernel had so much functionalities was somewhat unmanageable for the programmers. We have seen the simple structure of the operating system just before. We also saw the problems associated with such a structure. First of all, the hardware was not protected from user applications. Also, the interfaces between different functionalities of the operating system was not very clear. Further, a lot of functionalities were associated on a single layer, as was seen in the kernel structure of the original Unix operating system. The remedy to all these problems is to somehow modularize the structure of the operating system, or basically the kernel of the operating system. Modularization requires differentiating the functionalities of the operating system, associating related functionalities together, and providing clear interfaces between different functionalities. There are different ways of creating modular structure of the operating system. One of the ways is to use the layered structure. In the layered structure, the layer 0 is the hardware, after which there are different layers that come beyond it, and the last layer is the user interface, that is the user programs. In the layered structure of the operating system, each layer can only use the functionalities of the layer below it. The layer is an abstract concept. There is no existence of layer physically in the operating system. Layers, you can think of them as defined by specific functions and the data that these functions operate on. And therefore, communication between layers is also very clear. You only need to know about how the data is to be passed to the functions that are existing in a layer below the existing layer. Since there are clear-cut functionalities of each layer, changing any layer is very easy because you only have to think about the functions and data associated with that particular layer. And therefore, operating system can be easily extended. Again, since the layer 0 is the hardware and only layers can access layers just below them, there is complete protection of the hardware. However, this structure does not only have advantages, it also has certain disadvantages associated with it. First of all, we know that in the layer structure, we have the requirement of each layer calling just the layer below it and not those which are above it. Therefore, it is very important to describe what are the functionalities that are to be associated with a single layer. This is not as simple as it might seem to be, because different layers might need functionalities of very many different layers. And beforehand, when you are designing an operating system, it is not very easy to understand how these functionalities need to be divided so that each layer only accesses the functionalities that are provided by layers below it. Further, since there are a lot of layers associated with the operating system, even simple tasks require a lot of system calls. These system calls in effect reduce the speed of the operating system. So, the response of the operating system to an operation, the speed of it gets reduced because of this structure. Therefore, this structure was later changed and different possibilities were discovered. One of them is the microkernel structure. This structure was first implemented in the Mac operating system. The basic idea in the microkernel structure is to keep the kernel small. That is why it is called as microkernel. So, only the basic functionalities associated with the operating system are kept with the kernel, and all other functionalities are implemented as user programs. Now, what constitutes these basic functionalities? What should we consider as the basic ones and what should be kept as a user program? There is no clear consensus on this, and it is mainly dependent on the designer of the operating system. However, in the Mac operating system, the basic functionalities that were kept in the kernel were memory management, CPU scheduling, and some other functions. And all other functionalities were kept in the user domain. In such a system also, extending the system is easy because all the functionalities will be implemented in the user space. Again, we have clear-cut interfaces and there is protection of the hardware because user programs cannot directly access the hardware and there is microkernel in between. It increased the speed because the system calls that were required for accessing the hardware got reduced. However, since most of the functionalities were implemented in the microkernel system in the user space, it resulted into a lot of overhead on the system, and therefore, the performance of the system decreased even in this type of structure. As we have discussed that microkernel structure was first implemented in the Mac operating system. Later, it was also used in the Windows 95 systems. However, the performance levels were very poor in these systems, and therefore, when Windows NT systems which had their initial release in the microkernel system, Windows NT 4.0 systems, when they were developed, most of the functionalities of the operating system were again integrated into the kernel and the kernel was in a way made larger. Again, when Windows XP was developed, most of the functionalities of the operating system were kept again in the kernel. So, it was a microkernel structure, but the structure of the kernel contained most of the functionalities of the operating system. We have seen the problems that were associated with the layered structure as well as the microkernel structure. Perhaps the best possible way of implementing the operating system, and that is also the most frequently used method nowadays, is using the modular structure of the operating system. what do we do in the modular structure? Well, in the modular structure, as in the microkernel structure, there are certain functionalities that are kept with the kernel. The kernel contains the core functions related to the operating system. All other functionalities actually exist in terms of loadable modules. These modules can be loaded as and when required into the operating system. So, suppose if a module is not needed, that module will not be loaded and will not cause overhead on the operating system. The core functions associated with the kernel are again decided by the designers of the operating system, and rest of the modules and rest of the functionalities are given in terms of different types of modules. The figure that you can see here is that of the Solaris operating system. These are the Solaris loadable modules. Solaris was one of the operating systems that used the modular structure. The modules for the modular structure operating systems are designed using some object-oriented programming language such as C++. So, each module can be implemented as a class in C++. These modules, now we have seen that since the kernel again is having some core functionalities, this structure is similar to the microkernel structure. However, there is a difference. The functionalities that are provided as loaded modules in the structure give more flexibility to the system, as that can be integrated into the system as and when required, and therefore, this structure is more flexible. Again, this is similar to the layered structure because there are different types of modules associated with the structure. But as in the layered structure, we wanted the layers to access only the layers below it, which is not the requirement here. So, there is more flexibility. Each module can call any other module, and therefore, that requirement of the layered structure has been relaxed. Also, in microkernel systems, we had all the user level programs or the functionalities that were associated with the user programs required to communicate with each other through message passing. In message passing, when two functions or say two processes communicate with each other through message passing, they actually send and receive messages. These messages are sent and received with the help of the microkernel. This increases the overhead that exists on the system. In the modular structure, even though we have a kernel with core functionalities and we have loadable modules, these modules need not communicate with each other through message passing, and therefore, there is no system overhead. As I told you, this is the most common technology that is used for designing the operating system. So, most of the modern operating systems have this type of a structure. As you can see, all the modern implementations of Unix such as the Linux, the Mac OS X and Solaris have this type of structure.